All I did while the camera was off was just clear a little bit of board space. We had parametrized the half circle, and we had plugged that into f and then taken the derivative. We determined that the derivative was always defined, so any critical points would be where this derivative is equal to 0. Now, I purposely avoided using double angle formulas so that I've just got one angle in here. The only angle I'm looking to find is t. But I have two trig functions because I have sines and cosines. It's going to be a lot easier if I have one angle and one trig function. So I'm going to use my Pythagorean identity to rewrite cosine squared in terms of sines. So this is 4 sine t plus 4 sine squared t minus 4 times 1 minus sine squared t, and I want that to equal 0. Okay. So 4 sine t plus 4 sine squared t minus 4 plus 4 sine squared t, because I'm distributing the negative as well as the 4, I need that to equal 0. Let's see, that's 8 sine squared t plus 4 sine t minus 4 equals 0. Excellent. That is a quadratic in sine. Now, I think I'm going to just divide both sides by 4 so that I get some smaller numbers here. And let's see. We can clear some space. So when I do that, we get 2 sine squared t plus sine t minus 1 equals 0. At this point, I can either factor or use the quadratic formula. I'm going to factor because it actually factors quite nicely. In order to get 2 sine squared, I'm going to want to have a 2 sine t and a sine t. To get a minus 1, I'm going to want a 1 and a negative 1. Looks like I want the plus 1 here and the minus 1. So if these two factors multiply to give me 0, one of them is 0. Now if 2 sine t plus 1 equals 0, sine of t is negative 1/2. If sine of t minus 1 equals 0, sine of t equals 1. Both of these equations have infinitely many solutions, but I only want the one that's between negative pi over 2 and positive pi over 2. Okay. So that corresponds, of course, to quadrants 1 and 4. If sine is negative, we're going to be in quadrant 4. Okay. So we're talking about a negative acute angle. And of course, the reference angle is the acute angle whose sine is 1/2. So this is going to be t equals negative pi over 6. If sine of t is 1, that occurs at any angle whose terminal ray passes through this point. That's going to be when t is equal to pi over 2. Okay, so we have found our critical points. Now what I usually do is for each section of the boundary, I create a little subtable. So I'm going to have t, x, y, and f of x, y. And I want to make sure I indicate that I know I'm supposed to check two types of points: critical points and endpoints. Critical points will be when t is pi over 6 or pi over 2. My endpoints will be these extreme t values. Pi over 2 we've actually already got. It's both a critical point and an endpoint, but I would want to include negative pi over 2 as well. Now, if I look at my region D, which was this disk, the points when t is pi over 2 and negative pi over 2 are 0, 2, and 0, negative 2. They were also on that line segment. So I've actually already checked these points because they're just, well, 0, 2 is explicitly there. That was my critical point. And both of them have this form of 0, comma, y, where y is between negative 2 and 2. So I'm going to just include them here anyway because it's super quick to write them down and say, hey, f is 0 at those points. Okay. If I didn't include them here, well, I have to include pi over 2 because it was a critical point. But if I didn't write them on this table, I would have to say the reason I'm not checking my endpoints is because I already did. I am not a mind reader. On every portion of the boundary, you have to check two types of points, critical points and endpoints. That means you have to do that, or if there's a reason that you don't have to do it, like I already did, you have to say that. Okay, so let's see. At negative pi over 6, well, let's see. That's going to put me at cosine of negative pi over 6 is positive root 3 over 2, so this is just root 3. And then my y value is 2 times negative 1/2, which is negative 1. Okay. If I plug that in, 2x is 2 root 3, minus xy is minus a negative root 3, so that's another root 3. That's just going to be 3 root 3. These 2 points were already on the master table. I'm going to just add this additional point, root 3 negative 1, with 3 root 3, to my master table. And now I can see I've only got 2 z values to choose from here. Now, if you use a different parameterization for things, it's possible, in fact, it would happen if you used that x was this positive square root of 4 minus y squared, you could have additional points on your table. They just won't be the locations of the max or the min. Okay. So here I can see that's the biggest value, and that's the smallest value. So now I can say f has a max of 3 root 3. It occurs at root 3 negative 1. So that's the value, and that's the location. And then f has a min of 0, and it occurs at, don't need to list that point separately because it's included here, but I do need to name all of those locations. So at all points 0y, where y is between negative 2 and 2, including those endpoints. So that is the first problem.